for the test review here. 25 to 29. Let's talk about domain and range, and then kind of a challenge question. Determine the values of x that do not lie in the domain. Let's see. I have a rational function, 3 rational functions here. The hard part for these problems is remembering how do I compare the denominator to 0, right? We know that we're only looking, or we should know that we're only looking at the denominator here, and somehow that's supposed to compare to 0. But you have to remember, what kind of number cannot be the denominator? Well, the denominator cannot be equal to 0. That's why I'm going to set that denominator not equal to 0. It can be positive, it can be negative, any positive or negative number. It just can't be equal to 0. So you go ahead and you solve this for x. So I'd add 5 to both sides. We'll get 3x is not equal to 5, and divide by 3. So my set builder notation, when I write the answer here, we'll have my curly brackets. My domain is all x's, such that x is anything, but it's not equal to 5/3. And that's actually the domain, how you would write it. Okay? B here is similar. Now that we've got that down, ignore the numerator. The 2x in the numerator does not matter at all. We'll deal with that in pre-calc next year, not this year in Algebra 2. So I take my denominator and set it not equal to 0. Now the tricky thing about this one is there's a square. And what I've said in class is if there's a quadratic or a squared term that we're in our denominator, I have to actually factor the denominator. So we factor that to be x times x minus 3. This is GCF I just factored out of x. Then I take both of those factors and set them not equal to 0. I'm going to get 2 numbers this time that my x can't be. So I'll have x not equal to 0, that's one of them. And then x, I'm going to add 3 here. X cannot be equal to 3. So if I put that in set builder notation of all the x's, where x could be anything, but it can't be equal to 0 or 3. Now if you need to see why, look at your graph here of this function. Sorry, let me delete some things I was working on. If I graph that original function, which was 2x divided by x squared minus 3x. Here's the graph. Now we said my domain could not be equal to 0. And if I actually, it's hard to see from the graph, but if I looked at the table, for x of 0 it says undefined. There's actually not a value there, and if I zoomed in on the graph, well, sometimes they put like a little hole right here. You can't really see it, but there isn't a value at 0. Maybe if I undid the table. But there's no value at 0 right here. Like if I clicked on 0, it says undefined. There's a hole there. And then at x is 3, there's an asymptote, right? I lost my grid. But you can also see that from the table here. If I put 3 in, it's also going to give me undefined. Okay, so you can use your calculator to help you check your work. All right, last one for C. Again, ignore the numerator. Look at the denominator. I'm going to take this whole denominator and set it not equal to 0. That's not, the whole denominator can't equal 0. Again, I have a quadratic, so I have to factor. This is a trinomial, so I'm going to factor this. Get x and an x. 2 numbers that multiply to 8 and add to 6 would be 4 and 2. Then I set both of those factors not equal to 0. And solve. So subtract 2 on the one and get x is not equal to negative 2. Subtract 4, and x can't be negative 4. So my set builder notation tells me my domain for f of x is all the x's, where x cannot be equal to negative 4 or negative 2. But anything else in the world, my x could be. Okay, and the graph's going to look similar to that last one. All right, 26, still domain. This time I have a square root function. Now remember, we're going to take the radicand, the stuff under the radical, and we know we're going to compare it to 0. Now the radicand, the value under the radical, cannot be negative, so it has to be greater than 0. And it also could be equal to 0, right? You can take the square root of 0. That's equal to 0. So I'm going to set that radicand greater than or equal to 0. And all I have to do is solve for x. So I'll add 2 to both sides. And I'll get 6x is greater than or equal to 2. And divide by 6. So my set notation, notice it's interval notation, I'll get there, is all the x's, where x is greater than or equal to 1/3. Now, that would be the set builder notation. Here I want you to practice interval notation. And sometimes interval notation is hard to get to from an inequality. So if you need to, think about a picture. You have 1/3 here on my number line. And the domain, I can pick any number that's equal to 1/3 or greater than 1/3. That's my picture of my domain. Any x value that I choose, bigger than or equal to 1/3, I can put in for x in the original equation. So my interval here is going to say, okay, I can start at 1/3 and pick any number up to infinity that I want. Same idea for b. I'm going to take that radicand and set it greater than or equal to 0. So to solve this, I'm going to subtract 9. I'll get negative 3x is greater than or equal to negative 9. And then I divide by negative 3. Now, when I divide by negative 3 here, remember when I divide by a negative, I actually flip the inequality sign. And this would be my set builder notation. I want all the x's where x is less than or equal to 3. Now, just like the last problem, I do want to put this in interval notation. So I'm going to make a number line if I need to. Say, okay, here's 3. And for my domain, I can pick any number from 3 or anything that's less than 3, smaller. So my interval here is actually all the negatives and numbers up to or equal to 3 that I could put in for x in this original equation. I could put it in there. All right, now, which of the following values of x is in that domain? So in this interval, or in that inequality, which is the same, which numbers are less than or equal to 3? Well, negative 2 is definitely within that domain. 0 is less than or equal to 3, and 3 is equal to 3. 6 is not in that domain. Meaning, if I put 6 in for x up here, if I had the square root of 9 minus 3 times 6, I'd have the square root of 9 minus 18, which is the square root of negative 9, which we can't do yet. All right, 2 more, or 3 more, really. 27, find the domain and range. Now, this is not a continuous graph. It's not even a function, but it's not a continuous graph. So I can't do an interval. I need to list out the x values. So we have to use set builder notation here. Can't use interval. And I want all the x's. My domain is the only x's of 2, right? If I wrote the ordered pair here, I would have 2, 6. If you need to do that, go ahead and write your ordered pairs. Right? The x's that I listed are 2, 3, 6, and 7. Those are the only x values. I cannot write an interval from 2 to 7 because not every number is included. 5, 4, 6.12, that's not listed in those ordered pairs. So I have to just list the values. When I look at the range here, I'm doing the same thing, but with y's. Right? So look at all those ordered pairs. What y values do we have? I have 2, a 3, a 4, 6, and 7. That would be the range. All right, multiple choice here. Given the graph, what is the range? Now I put a couple different notations here, interval and set builder, so you can read it. My range, think about the graph first. Range goes from bottom to top. Bottom has an arrow, the top maxes out at 3. So I'm going, if I want, I can write it as an interval notation here and see which matches. The bottom is from negative infinity up to 3. So it's definitely not all real numbers because I cap out at 3 and not including all positives. B looks similar, but B has a parenthesis here, so that can't be right because I'm including 3. D, same thing, I have a bracket on infinity, that's not right. C is actually the correct way to think about it. All the y's less than or equal to 3, which is the same value. All right, now 29 has multiple ways to do this problem. You do not have to do your graph the same way that I did my graph. This is just helping you think about it. And a strategy. It says we have a domain of -8 inclusive up to 6 non-inclusive. The way I like to do this is I'm going to draw on my graph. So -8 I have to include. So I'm going to put a solid line at x equals -8. So I know that I have to include a value on that line. And I have to go up to 6, but I can't include it. So I'm going to put a dotted line there. That's just my visual cue. I have an absolute maximum value at 5. So 5, y, that's a y value. I have to include 5, but I can't go beyond that line. I have an absolute minimum at 3, -6. So I can't go beyond this line, -6, but I have to include the point 3, -6. That's the lowest point on my graph. I have a y-intercept at 2, an x-intercept at -6. Oh, and there's one more, increasing from -8 to -4. So here, between -8 and -4, I have to increase. All right, so other than that, you can make your graph, other than those 6 things, you can make your graph however you want. So let's see, I'm going to start, how about I put a solid dot here. I'm going to increase here. Actually, I'm going to go all the way to the top. I'm going to hit my absolute max here. Why don't I come down through my y-intercept to my x-intercept, and then I just have, maybe I'll have an open dot right there on x. Your graph doesn't have to look like that. You can squiggle more, you can change directions at different points, hit your absolute maximum at a different point, but that's one idea.